Hi guys, welcome to lecture 34. Today we will be discussing calorimetry. So last time we were talking about heat and work and heating up different objects, heat capacities. Calorimetry is really the study of how we measure those heat capacities and how we measure enthalpies of reaction. So I'm going to start with a question that I think will get us in the right mindset here for discussing calorimetry. Let's say that we have a 20-gram piece of iron being forged at 1000 degrees Celsius, and we drop that into 1 liter of water at 25 degrees Celsius. What is our final temperature of the water and iron? Now I have the heat capacity for the iron here and the heat capacity for the water. Notice that water has a much higher heat capacity, nearly 10 times the heat capacity of iron. So what we know here is that the temperature at the end has to be the same for iron and water. For them to be at equilibrium, they have to be at the same temperature. So our final temperature is going to be the same for both. And we know the heat lost by the iron is going to be equal to the heat gained by the water. Mathematically, what that means is that we put a negative sign in front of the heat of the iron because the iron is losing heat, and we have a plus sign in front of the heat of the water because the water is gaining. Now we can substitute our known equations for heats here. So the heat, as we remember, is equal to our mass times heat capacity times change in temperature. So on the left side here, we have the mass of the iron times the heat capacity of the iron times the change in temperature of the iron. And on the right, we have the mass of the water, the heat capacity of the water, and the change in temperature of the water. Now, on this particular slide, I have put subscripts for the change in temperature of the water and the change in temperature of the iron. Most of the time, we don't actually do that. We're not very careful with that. You're just going to have to remember that these guys change temperatures or have different changes in temperature. They're both going to finish at the same final temperature, but the iron is starting at 1000 degrees Celsius and our water is starting at 25 degrees Celsius. So our change in temperature is just our final temperature minus our initial temperature. So we have the same final temperature. Now we have all these other values. We know the mass of the iron, the heat capacity of the iron. We know those values for water. So we're going to need to solve for our final temperature. And the way we're going to do that is we're going to have to distribute the things outside the parentheses to inside the parentheses. That means I'm going to have to multiply my MC times my T and my MC times 1000. So it'll look like this. So this is negative MC times T final plus MC times T initial. Why is this plus here? Well, because we have a negative times a negative. Those give us a positive. So that's the same on both sides here. Then what we're going to have to do is we want to get our final temperature all on one side. So we're going to take this negative value, we're going to add it to both sides. So that'll move that over here. We'll take this negative value, add it to both sides, so it'll move over here. Now we have our final temperature all on one side, and then we can factor that out. What that'll look like is this. So we'll have the MC for water plus the MC for the iron times the final temperature. Now we can just start plugging values in here. Now in our question, we have the grams of iron. For water, that's given in liters, but like we talked about last time, 1 gram of water is equal to 1 milliliter of water. 1 liter of water is equal to 1000 milliliters. That means it's also equal to 1000 grams. So now we have our mass, our heat capacity, all our temperatures. We can plug that in. And I'm just skipping all the plugging in of numbers, going right to the answers here. But then we can just take this number on the right side of the equation and divide it over onto this side. So we get these two added up divided by these two added up, and our final temperature is 27.09 degrees Celsius. Make sure you follow all of these steps. Make sure you can do a problem just like this when asked. Right? Because this is that question I was going to ask you in class. We have 1 kilogram of hot iron, which has a heat capacity of 0.450 joules per gram times degrees Celsius. We're starting at 200 degrees Celsius. We drop that into a bath of water. The water's heat capacity is there. And the water's starting at 25 degrees Celsius. What is the minimum volume of water necessary to contain the heat without boiling the water? Okay, if you want to pause here and try and work this problem yourself, you're free to. All we got to remember is that energy will flow from the iron into the water. That means we're going to put a negative sign in front of our heat of our iron, and a positive in front of the heat for the water. We're going to substitute our MC delta T equations in here. Now you'll notice that the delta T does not have subscripts for water and iron, so always just remember that they almost always change by different amounts of temperature. So here though, again, we're solving for one of these values. In this case, we're actually solving for the mass of the water. It asks what's the minimum volume of water, but since we know the relationship between volume and mass for water, we can just solve for the mass of the water. Okay, so we can plug in our heat capacity for the water, our heat capacity for the iron, and the mass, etc. Or sorry, yeah. But notice in the equation for delta T, the water is starting at 25 degrees Celsius going all the way up to 100. So this is the change in temperature that we need to get water to its hottest point right before it starts its phase transition. So you can get water to 100 degrees Celsius without causing it to boil. But at this 100 degrees, if you put any more energy into it, then it'll start to boil, but stay at 100 degrees. So our delta T for our water is 100 minus 25. And our delta T for the iron is 100 minus 200, because the iron is starting at 200. But it has to equilibrate with the water, go down to 100 degrees Celsius. All right, now it's just simple math. We take this guy and divide it over here. So for our mass of our water, we find that we need 143 grams to contain all the heat from this 1 kilogram of hot iron. And 143 grams equal to 143 mils of water. When we take sig figs into consideration, we find that it takes 140 mils of water. If you have questions about that, let me know. But hopefully you're getting the idea of how we're measuring heat capacities and the heat released by reactions. We really just stick them in water most of the time, see how much the water changes in temperature. So specifically how we do that is we start by raising some substance to a specific temperature, a known temperature. So the way I'm showing that here, one way of doing it is you take a known amount of your substance, put it in some test tube. So here we're saying we have 25 grams of some metal. We put that in a beaker of solution. In this case, we're boiling that solution, which is a really convenient way to set the temperature really precisely, since water boils at 100 degrees Celsius. If you stick this sample in boiling water, you can equilibrate it to 100 degrees Celsius. Then, once this has been heated to a known temperature, we're going to take that and put it into a closed system. So here in this closed system, we just have styrofoam cups and a lid. But what we do is we have a closed system with an insulator so that heat's not escaping. And we fill this with a known amount of water. So here we're saying we have 50 grams of water. And we stick a thermometer in there and measure the initial temperature. So this one is starting at 19.3. Then we take our hot substance and we dump it in. So you can see down here that we have our metal. Then we let that transfer its heat to the water. And then we measure the final equilibrium temperature of the water, which in this case would be 27.1 degrees Celsius. So now we know the mass of our substance, we know the mass of water, we know the heat capacity of water from previous measurements. And then we just measure that change in temperature. Now we have all the pieces we need to set up an equation that looks like this, where we say the heat given off by the substance when it's put in the cold water is equal to the heat gained by the water. And then we can substitute in our MC delta T equations for our two different heats there. And now we know everything. We know our mass, we know our change in temperature for our substance, we know our mass, our heat capacity, and change in temperature for the water. Then we just have to solve for our heat capacity of the substance. And that's really all there is to this. But we don't like to use a bunch of styrofoam cups in a lab, especially because that's really dangerous. What if you spill your hot water on yourself? Or what if you spill this 100 degrees Celsius metal on yourself? So we usually do this in a better sealed container that we call a bomb. So a bomb calorimeter looks like this. So it has an insulating casing. It has a bunch of water inside, and it has an inner container where we put our reactants. And we have these wires in here that we use to spark or ignite our reactants to get the reaction starting. And we have a thermometer in here to measure the temperature of the water. And then oftentimes it'll also have a stir. That'll just help the water mix. It'll help it reach an equilibrium temperature a little faster. So we put our food in this sealed container. And we also want this container to be as conductive as possible. So we usually use some metal. That way it'll reach equilibrium with the temperature inside more quickly. And that'll help it also to reach equilibrium with the water more quickly. We ignite the food. So sometimes it will explode. A lot of times it'll just burn. Then we set the heat of the heat given off by the reaction equal to the heat absorbed by our calorimeter. And then we say that our heat given off by, or we substitute the heat of the calorimeter for the heat capacity of the calorimeter times the change in temperature. Now this heat capacity is not just the heat capacity of some amount of water. Usually what we will do is find the actual heat capacity for the entire calorimeter. That way we don't have to worry about measuring out the volume of water very specifically, and we don't have to worry about a few other things by doing it that way. And then we just run our calculations. So the first thing we have to do though is figure out what our heat capacity of our calorimeter is. So the way we do that is just like this. So we burn some amount of some substance with a known heat capacity in our calorimeter and watch how much the temperature changes. So for example, if we want to find the heat capacity of this calorimeter, we'd burn a 1 gram sample of benzoic acid, and we'd measure the amount it changes its temperature of the calorimeter. So that changes the calorimeter's temperature by 7.248 degrees. And we know that combustion of benzoic acid releases 26.38 kilojoules of energy per gram of benzoic acid. So then we just set up our equation like before. We say the negative heat given off by our reaction is equal to the heat absorbed by our calorimeter, and that's equal to the heat capacity of our calorimeter times the change in temperature of our calorimeter. This C right here, the C of our calorimeter, is what we're looking for. So we're just going to solve for that. So C will just be equal to Q divided by delta T. We have Q from our problem. It says that we gave off 26.38 kilojoules of energy per gram. We only started with 1 gram. So our heat given off is 26.38. And our change in temperature is also given in the question. This change in temperature is just 7.248 degrees Celsius. So when we divide those out, we find that C in this case is 3.640 kilojoules per degree Celsius. Let's practice that one more time. So in this question, we are asking the combustion of a standard releases 100 kilojoules of heat and raises the temperature of the calorimeter by 14.8 degrees Celsius. So what is the heat capacity of the calorimeter? So notice in this case, I don't say how much of the standard was burned or how many moles. I'm just saying that it's giving off 100 kilojoules. You want to try and solve that problem out by yourself real fast, go ahead and pause this video. We again set the heat given off by our reaction equal to the heat absorbed by our calorimeter and set that equal to C delta T. We again just solve for C, so C equals Q over delta T. Make sure that you use the right Q. You don't want to use the negative Q of the reaction. You want to use the positive Q of the calorimeter. Then you just divide that out and find that the C value is equal to 6.76 kilojoules degrees Celsius, or per degree Celsius. Okay, let's give another calorimeter practice problem. Let's say that we've already found the heat capacity of our calorimeter. We found it to be 7.794 kilojoules per degree Celsius. And the temperature of the calorimeter increases from 25 degrees Celsius to 39.5 degrees Celsius when a handful of peanuts are burned in it. I want to know from you how much heat in kilojoules is generated. And then once you have that in kilojoules, I also want you to give it to me in calories. We're going to work that problem is the same as we've worked them before. We'll start by acknowledging that the heat absorbed by our calorimeter is equal to the heat capacity of our calorimeter times our change in temperature. So we have our heat capacity of our calorimeter, that's just 7.794. And our change in temperature will just be 39.5 minus 25. That'll be 14.50. We'll just multiply those two numbers together and find that we got 113 kilojoules of heat. Now I also wanted that in calories, so we're going to have to divide this number by 4.184 to get us 27.01 calories. Now some of you might be asking, well, I thought this, or 4.184 was for going from joules to calories. Well, you're right. It is for going from joules to lowercase calories, but that 4.184 ratio also works for going from kilojoules to capital case calories. I know that can be a little confusing, but make sure you can get that straight. So 4.184 will take you from joules to lowercase calories, and 4.184 will take you from kilojoules to uppercase calories. Let's say now that we want to find our change in enthalpy for a reaction using calorimetry. So in this case, we use a special calorimeter called a constant pressure calorimeter. These are just designed so that the pressure internally doesn't change. We're not going to worry in this class about how to design those. But let's say we put 1 mole of methane in our combustion chamber and we react that with excess oxygen at constant pressure. And our calorimeter has a heat capacity of 7.794 kilojoules per degree Celsius. And the temperature of the calorimeter changed by 102.9 degrees Celsius. What is the change in enthalpy per mole for the combustion of methane? So we're going to work this problem very similarly to how we've done it previously. We're going to say that the heat given off by the reaction is the same as the heat gained by our calorimeter, but then we're going to have to make some substitutions. So if you remember from our discussion about enthalpy, if we're at constant pressure, then our enthalpy, our change in enthalpy is just equal to the heat given off by your reaction. So Q, in this case, would be equal to delta H. Then for the Q of the calorimeter, we'll again just set that equal to C delta T. Now we can plug this value and this value into this equation. We'll move the minus sign over here for convenience. So delta H is just equal to, so delta H of the reaction is just equal to the negative C of the calorimeter times our delta T. We just plug those numbers in and we find that our delta H for this reaction with 1 mole of methane is negative 802 kilojoules. But what if I was going to ask that same problem, but instead we're combusting 2 moles? Well, then in that case, we just take this value for 1 mole, times it by 2, and we get negative 1,604 kilojoules. Okay, I'll give you one more practice with that problem. We say 1 mole of butane is combusted with excess oxygen in a constant pressure calorimeter, and that calorimeter has a heat capacity of 20 kilojoules per degree Celsius, and the temperature of the calorimeter changes by 144 degrees Celsius. What is the change in enthalpy per mole for the combustion of butane? If you'd like to pause the video now, go ahead and try to work that problem. Okay. Again, we're going to make those exact same substitutions we made on the previous slide, where we're going to say the heat lost by the reaction is equal to the heated calorimeter. The reaction is equal to the enthalpy of the reaction. We're going to also say that the Q for the calorimeter is equal to C of the calorimeter times our delta T. Plug these values into this equation, and we'll find that delta H is equal to our negative heat capacity for our calorimeter times the change in temperature, which is just negative 2,880 kilojoules. Now, when we take sig figs into account, we're going to have to round that to 2 sig figs. So our answer will be A, negative 2,900 kilojoules per mole. This video is pretty short. Hope you're happy about that. You can use your extra time for twiddling your thumbs or writing a sonnet. All right. Hope you guys are all still doing really good. You guys have a good day.